Thanks. So I'll continue the trend. I'll talk about query complexity, lower bounds, upper bounds, and trying to sleep well at night. That's the goal of this talk. So firstly, this is based on two works. The first work was with Job Briet and Carlos Palatuelos. It appeared over a year back in archive. And the second work is with Sandro Gribling and Monique Laurent, and it appeared earlier today. Right. So the goal of quantum computation is to understand the power and limitations of quantum algorithms. And that's something we'd like to understand. And we do know of some areas where quantum resources are known to help. For example, if you look at communication complexity, we know that there could be exponential advantages for certain tasks. Then there's learning theory, there's query complexity, and cryptography. And in all these areas, we do know that quantum resources do provide some advantage. And in this talk, I'll be focusing on query complexity. And in particular, I'll be looking at the classical and quantum query model. And why do I look at this model? First thing is easy. It's easy to state. It just takes me a few lines. And secondly, almost all algorithms that we know right now are expressible in the query model of computation, for which we can either show a polynomial or exponential advantage, and it is provable. So that's interesting. So the next couple of slides I'm going to spend on introducing a classical and quantum query model, but it's been introduced twice, so I'm going to go through it slightly quickly. So the central object here is a Boolean function. F is just a function that maps n-bit strings to a bit. And unlike the previous talks, I'm going to take a bit strings as plus minus 1 to the n to plus minus 1. This is just for simplicity. Right. So the goal here is I have an x. Everybody knows an f, but I have an x unknown to you. And your goal is to compute f of x. And the way you're given access to the unknown x is you can make queries to me. And what do I mean by a query? If you ask me I, I'll tell you what's xi. So if you ask me 7th bit of x, I'll tell you x7. And we keep repeating this. And eventually, your goal is to compute f of x. Of course, one strategy is you just ask me what's x1, x2, x3, and we go all the way to xn. You know x completely. You know f. You know f. And you can compute f of x on your own. So that's a simple strategy. And the goal is to see if there is something more efficient to be done. And I'm just going to denote d of f as the deterministic query complexity. That is what is the hardest input that I could have that could force you to make a certain number of queries to compute f of x. And there are other models of computation, such as randomized query complexity, non-deterministic query complexity, unbounded error query complexity, and quantum query complexity. And each of these models, there are certain restrictions you could place on the learner. Either he could be quantum, or you could say maybe he doesn't need to compute f of x every time. He just needs to compute f of x with some probability, and so on. But in this talk, I'll be focusing on quantum query complexity. And let me define the quantum query model. So earlier, you could ask me what's I tell you xi, but now you could ask me a superposition of i's. I give you back a superposition of I comma xi's, and that is precisely what is the advantage of quantum query complexity. So this model of query that we have is going to be replaced by quantum query. That's this unitary OX. And it's just going to act on two registers. The first one is called control. The second one is called query. The control is either 0 or 1. And if it's 1, it's going to apply a xi in the face. And if it's a 0, OX does nothing. So this is just how I'm defining a quantum query. And let me give you a simple what a D-query quantum algorithm is going to look like. So it's going to have three registers, the control and the qubit, and the W. That's the workspace. The control is on, the oracle acts on two registers, C and Q. That's the 1 and I, or 0 and I. And the unitary could act on a workspace. That is just some extra computation if the unitary wants to do something. So the D-query quantum algorithm is going to have a unitary, oracle, and it repeats this D times. It makes a measurement in the end, and the output's a bit plus or minus 1. So this is how a D-query quantum algorithm looks like. And we say this algorithm computes a Boolean function f if it satisfies the following property. So this algorithm A was just this. After making D queries, it makes a measurement in the end. We would like that the output of the algorithm, that is this, is equal to f of x with a certain probability. And this should hold for every x. So for every x, after making these D queries, it should output a bit which equals to f of x with high probability. So if you want to give, and the quantum query complexity is, as always, the worst case input, and you look at the minimal number of quantum queries that you need to make on the worst case input. So to give upper bounds on Q of f, it's easy. You just construct these unitaries, U0 to UD, and you say, OK, when I construct these unitaries, it satisfies this equation. So that's a quantum query algorithm. So that's nice. So constructing quantum query algorithms essentially just boils down to constructing these unitaries. And almost all these algorithms that we know for period finding, Shor's algorithm, Grover's algorithm, Nant tree evaluation, almost everything can be rephrased actually in this model of computation. But what I care about here is what about lower bounds? What if I want to say, like, let's just say Grover's algorithm. We know that square root 10 number of queries suffice to satisfy this condition. But is square root 10 optimal? Is there fewer number of queries that I can make that still satisfies this condition? And for that, we need to rule out every possible setting of these unit trees that could possibly satisfy this condition. And that is what you want to give lower bounds on quantum query complexity. And to give lower bounds, there are two extremely well-known methods in quantum query complexity. One is the polynomial method, and one is the adversary method. The polynomial method was introduced in '98 by Beals, Berman, Cleve, Mosk, and de Wolf. I just couldn't find a photo of Beals. I mean, on Google, even de Wolf, Ronald couldn't find a photo, so I don't know. And the key idea is the following. Efficient quantum algorithms give you low-degree polynomials. That's really about it. It's a beautiful connection that says, look at quantum query algorithms, and they connect it to something that seemed totally unrelated, low-degree polynomials. So let me tell you a little bit more about what the idea here was. Recall, this is a D-query quantum algorithm. Let's just forget this for now. It's just a D-query quantum algorithm that outputs a bit plus or minus 1. And the idea is, let's just say you make a D-query quantum algorithm, and this, let's just say after making this measurement, before making this measurement, let's just say it's a random variable. The random variable takes value plus 1 or minus 1. Each has a probability p, p1 or p minus 1. So what they said is, if you look at the expected value of this random variable, you can write it as a polynomial. But not only that, this polynomial has degree 2D. So if you have a D-query quantum algorithm, you get a polynomial of degree 2D. And this polynomial depends on the variables x1 to xn, and is multilinear. That is, every monomial just has terms of the form x1, x2, x3, x4. It doesn't have powers of x's. And supposing this algorithm does a good job in computing the Boolean function f with some error, then what follows is the fact that this polynomial, let's just say this polynomial is this expected value of this algorithm. You would like the algorithm to do a good job. So the expected value, because this was true, you want the polynomial is close to f of x on all the inputs. So this is really their insight. If you have a D-query quantum algorithm, you get a degree 2D polynomial that satisfies this condition. Based on this, they looked at something called approximate degree. So the approximate degree is defined as follows. Let f just be a Boolean function that could be partial or total. When I mean by total, that means it's equal to plus or minus 1 to the n. When I mean by partial is the function is just defined on a subset of the Boolean cube. And let me define approximate degree first. So it's the minimal degree of a polynomial p that satisfies certain conditions. 1, p is just a polynomial on x1 to xn. 2, on the relevant variables, that is when f is defined, we want the p of x should be close to f of x and close up to error 2 epsilon. And the third thing is the fact that the polynomial is bounded. That is, whenever I feed in an input x from plus minus 1 to the n, this polynomial should take value at most 1. So let me reiterate. The approximate degree is just you find the minimal degree of a polynomial that is close to f. So if f was 1, this polynomial should be between 1 minus 2 epsilon and 1 plus 2 epsilon. And if f was minus 1, this polynomial should be between 1 minus 2 epsilon and minus 1 plus 2 epsilon. And the polynomial should just be bounded on the entire Boolean cube. And the key insight of what Beals et al. Did was they showed that quantum query complexity is at least the approximate degree of the Boolean function divided by 2. And this has had many applications, this lower bound. I mean, they reproved firstly Grover's lower bound, and then later was shown to reprove collision, like the element distincts lower bound. And even last year in QIP, there was this Kotari-Thaler paper where they give lower bounds on quantum query complexity and using lower bounds on approximate degree. So this has found many, many applications in quantum query complexity. So let me look at the second method of lower bounding quantum query complexity. It's called the adversary method. And this was shortly introduced after the polynomial method by Ambinus. He defined a combinatorial quantity called ADV that gives a lower bound on quantum query complexity. And a few years after that, Hoyerly and Spalek, they gave a better lower bound on ADV that still is a lower bound on quantum query complexity. So it sits between ADV plus minus, and it's the lower bound on quantum query complexity. And after this result, there was a question whether not only is this a lower bound on this, is this also an upper bound on this quantity? So there was a series of works, and after a sequence of results, Ben Reichart showed that ADV plus minus is equal to theta of quantum query complexity. So for every epsilon greater than 0, if you want to understand quantum query complexity, it is necessary and even sufficient to just understand ADV plus minus. So that's really the power of the adversary method. So really the adversary method characterizes quantum query complexity completely. So that's nice. So, okay, so we have two methods, the polynomial method, the adversary method. The adversary method is equal to quantum query complexity for every up to constants. The question is, does the polynomial method admit a converse? So what's the first natural question to ask? We showed earlier that Beals et al. Showed approximate degree is a lower bound of quantum query complexity. So is approximate degree a lower theta of quantum query complexity? Does this also give you an upper bound on quantum query complexity? And the answer is no. So Ambinus in 2004 showed there is a polynomial separation between approximate degree and quantum query complexity. So that's not good. A few years back, Aronson and Ambinus defined a new measure called block-multilinear degree. And what was nice, I'll define this measure later, but what was nice about this is it sits between approximate degree and quantum query complexity. And a natural question they asked is block-multilinear degree equal to quantum query complexity up to constants? And the answer is again no. So again, a couple of years back, Aronson et al. Gave a polynomial separation between block-multilinear degree and quantum query complexity. Right, so far these two measures haven't done the job in characterizing quantum query complexity. And the question that I want to really understand today is there a refinement of approximate degree that characterizes quantum query complexity? Or in other words, does the polynomial method admit a converse? And as the title suggests, it does admit a converse. And so there is a refinement of approximate degree, which is equal to quantum query complexity. So let me define that right now. And we call it the completely bounded approximate degree. So let f just be a function that's either total or partial, and that takes values to plus or minus 1. Let epsilon be a number between 0 and 1. The completely bounded degree is, again, the minimal degree of a polynomial p. That's a polynomial on n plus 1 variables. And something that we would naturally expect, that it should be close to f of x. So let's just feed the last variable 1. So p of x comma 1 should be close to f of x. And what I mean by close, it should be close up to epsilon. And this should hold for every input in the domain of f. So up to now, this was almost similar to what was happening in approximate degree, except this n plus 1 to n, which is not important here. So everything is the same. So what is the extra condition that we put? So recall that in approximate degree, what did I want? I said the polynomial is just bounded. On the entire Boolean cube, it should be between minus 1 and 1. But I'm going to put something that's funny. I'm going to say the polynomial should be completely bounded. I'm going to define completely bounded later. But let's just say for now we have completely bounded degree. This is how I'm defining it. And the main result of this talk is the following. So if you have f, that could be either partial or total. Epsilon could be 0 or between 0 and 1. The quantum query complexity is equal to completely bounded approximate degree. I'd like to make a couple of remarks here. The first is, so we know that adversary method also is equal to quantum query complexity, but that was only up to constants, whereas our degree measure is equal to quantum query complexity. The second thing, the adversary method is equal to quantum query complexity up to constants only for epsilon greater than 0, whereas ours also works when epsilon is equal to 0. So it truly admits a converse to the, yeah, this is cool. Right, so in this talk, I'm not going to prove this theorem because I don't think it's going to give you much intuition, but I'm going to give you why we even thought about coming up with this completely bounded notion. So that's what I'm going to spend the next few slides on, telling you how we even came up with this notion in the first place. And for that, we need to go back all the way to the polynomial method. Let's just go back to what Beals et al. Observed, but look at it slightly more closely. So let f just be a Boolean function that takes n-bit strings to plus or minus 1. Let epsilon just be greater than or equal to 0. Everything that I'm going to be saying for the next couple of slides also works for partial functions, but I'm just restricting to total functions for simplicity. So what did they observe? They said, this is a D-query quantum algorithm, unitary oracle, keeps repeating. You make a measurement. They observe that this measurement is a random variable, but this random variable is a bounded polynomial. That's really their key idea. You have a D-query quantum algorithm. It gives you a degree 2D polynomial. And they defined they use approximate degree to lower bound quantum query complexity. So let's again recall what's approximate degree. You want to find a minimal d such that there exists a degree d multilinear polynomial that takes Rn to R, and it satisfies two natural conditions. The first one is p of x should be close to f of x for every x. And this just translates to the fact that p is a good approximator of f on the entire Boolean cube. And the second condition that the approximate degree enforces is the fact that this polynomial is bounded. It takes value between -1 and 1, so for every x in the Boolean cube. And this just says that p is bounded. And the whole idea of Beals et al. Was to show that quantum query, if you have a d-query quantum algorithm, you're going to get a bounded polynomial, so it's going to satisfy both these conditions. So if an algorithm did a good job, it's going to give you a polynomial that's close to f of x here, and this polynomial is bounded because it's just end of the day of probability, the expected value of a random variable. So they observed this inequality that approximate degree is upper bounded by quantum query complexity. So next, let me look at the second thing that Aronson and Ambinus defined a few years back, and that's called the block-multilinear degree. And they observed something that's nice is the following. Look at the standard quantum query algorithm, but initially they had unitary oracle, and so on. But let's just say we don't, instead of having an oracle for one string x, let's just have an oracle for a string x1, superscript 1, that's a n-bit string, x superscript 2, x superscript d. Sure, I could do whatever I like. And they said, let's just look at this. This made a lot of sense. So essentially what they're doing is replacing the oracle ox by different strings oxi. And their key observation was, you don't get a polynomial here, but you're getting a tensor, and it's bounded. So they and that led them to define the following notion of degree called the block-multilinear degree. And the block-multilinear degree is defined as follows. So you want to find the smallest d, such that there exists a 2D form. So form is just a homogeneous polynomial that takes in 2D copies of Rn plus 1 and outputs a real number. So if you're slightly not uneasy about the using of a 2D tensor, just think of a matrix as a 2 tensor. It takes in two values. A of x comma y just tells you an entry. You could think of a cube that takes a of x comma y comma z, enters a value. And if you just extend this naturally, you get a tensor. So that is what is a 2D tensor. Or 2D form is just a homogeneous polynomial. And the way they define this block multilinear degree is they required it to satisfy two properties. One, the natural thing. This tensor should be close to the Boolean function you're trying to compute. So what do I mean by that? Let's just say I feed in the tensor x comma 1, which is x is an n-bit string, x comma 1 is an n plus 1 bit string. So I feed in 2D copies of x comma 1, x comma 1, x comma 1. It should be close to f of x, and it should be close up to error to epsilon. So this just says that the t, this tensor, serves as a good approximator for f. And the next thing that they observe, which is the most crucial part, is the fact that this tensor, not only is it a good approximator of f, when I feed in arbitrary Boolean strings, y1 to y superscript 2d, which are n plus 1 bit strings, this tensor should still be in the interval -1 and 1. And what this means is t is just bounded. So what's the intuition behind defining this notion? If you have a d-query quantum algorithm, they realize that you're getting a bounded 2D tensor that satisfies the following. Let's just say I replace this ox1 by ox. That is just a standard quantum query algorithm. That is, if I replace all these xi's by the same x, that is what was happening before. So the point is, this does a good job in computing f, and that just translates to here. But let's just say I didn't replace the x1 to xd by the same x, but I just left it the way it is. End of the day, this is still a random variable that takes value +1 or -1 with some probability, so it is bounded still. And what they define is, what they realize is, the block multilinear degree is still a lower bound on quantum query complexity. Right. So initially we had ox all the way, and Aronson and Ambinus realized that you can put oracles for different strings here. That's cool. So let's try something more. So what's a natural generalization of this? Just put arbitrary unitaries. Why does it even need to depend on ox1, ox2? Okay? You can do whatever you like. So this is what we did. So look at a d-query quantum algorithm, and I'm just going to say it's unitary, another unitary, another unitary. Keeps going on. But of course, if we want this quantum algorithm to do something interesting, we have to enforce some conditions out of it. And the conditions that we are enforcing here is One, if these VIs are equal to the oracle OXs all the time, so it's OX, OX, OX all the way, then this is a standard quantum query algorithm, so this expected value should be close to f of x. That's the first condition that we want. But even otherwise, let's just, as what Aronson and Binus realized, you don't need to enforce this condition. VIs could just be arbitrary. But then end of the day, you're going to get a random variable here. So the expected value still has to be bounded by, should be at most 1. So this might be coming up a little early, but maybe you'll realize in the next slide what I mean by completely bounded tensor. So I'm going to try mathematically define what I'm trying to say in these two slides here. For that, we again need to go one step back. Let's look at block multilinear degree slightly more closely in order to, mathematically write these two statements down. So this was what Aronson and Binus did. They looked at this quantum query algorithm, which had oracles for different strings, x1 to xd. And just recapping their notion, block multilinear degree, you just want the smallest d, for which there is a 2D tensor that satisfies this. It takes 2D copies of Rn plus 1 and gives you a real number. And it satisfies that when these oracles are the same x, it should be close to f of x. That is, it is a good approximator of f. And secondly, this tensor, when you feed in arbitrary bit strings y1 to y2d, it should be a number between -1 and 1. That is, t is bounded. So I'm going to write this thing out slightly more in a fancy way. And the way I can write it out is as the following. So just this inequality, that's t y1 to y2d is plus minus 1, can be written down as follows. You can just believe me for it for now. OK, now let's look at what we define. We define this notion where OX1 is replaced by V1, OX2 is replaced by V2, and we keep repeating this. And we're going to define my new degree notion now. And the way it's going to be defined is, I want to find the smallest d, for which there again exists a 2D tensor that takes 2D copies of n plus 1. And it should satisfy the following. This is a natural condition. When I replace V1 by OX, V2 by OX, up to VD by OX, this tensor should be close to f of x. And all that this is saying is it should be a good approximator of f. And more importantly, we are going to enforce another condition. We're going to say t should be not only bounded, but it should be completely bounded. So what do I mean by that? Is the following. So for every k, and for every k by k unitaries wg of I want this condition. OK, before I tell you what the condition of completely bounded is, so the intuition here is the following. So y1 of y1 is a bit string. y1 of I1 is just a bit. Let's just replace this by matrix, w1 of I1, because that's what I'm doing here. I'm replacing bit strings by matrices, bit strings by matrices. So replace w1 of I1 by y1 of I1 by w1 of I1, and I keep doing this. But this was a bit, this was a number between -1 and 1, and we enforce this condition. But this is now a matrix. It's no more a number. So this is the condition I'm going to enforce, that the operator value of this matrix is at most 1. So I say a tensor T is completely bounded if it satisfies the following condition. For every k, and k by k unitaries wg of I, if I look at this expression, it should be at most 1. If this expression looks slightly complicated to you, you could also think of it this way. You could write it like this. It's just t of w superscript 1 to t of w superscript 2d. It should be between -1 and 1. But recall that when I replace this by w1 up to w2d, it's a matrix now. So you should look at the operator norm of the matrix, and it should be at most 1. So this is really the new notion of degree that we're going to define. This is the completely bounded approximate degree. And going back to the main theorem that we proved, so we said, let's define this notion of completely bounded approximate degree. Right, so I'm cheating here. I mean, the previous slide I was talking about tensors, but now I'm suddenly talking about polynomials. So for every polynomial p, you could look at the unique symmetric tensor that's associated to it and look at the completely bounded norm of that tensor. So that's how we are defining completely. I mean, end of the day, we want a converse to the polynomial method. You don't want a converse to the tensor method. So we define for a polynomial, we look at the unique symmetric tensor. We define the completely bounded norm based on that tensor. And we are defining this as our entire completely bounded approximate degree. And this was our main theorem that says that if you look at the completely bounded approximate degree, it is equal to quantum query complexity for every epsilon greater than 0. And I'm not going to be going through the proof of this, but this proof crucially uses something that it's a seminal result of Christensen and Sinclair in C-star algebras back in 1987. And this essentially just generalizes time spring representation to multilinear forms. So what they showed is if a tensor, if a polynomial satisfies this, there's a nice way to represent this in C-star language. And what we did is essentially just understand the C-star language better and churn out a quantum query algorithm. And it so happens that you can prove that you can prove both upper bound and lower bound here. So again, the intuition was you have a quantum query algorithm, you replace the oracles by oracles for different strings. That's what Aronson and Ambinus did. And we said, let's go one step further, replace this arbitrary strings by arbitrary unitaries altogether. And that's how we got this notion. Right, so I'm going to be talking about one other result that was also presented by Aronson et al. And so let's look at the result of Beals et al. Back again to 98. What did they show? What they showed is if you have a D-query quantum algorithm, you get a degree 2D polynomial. Okay, that's really the polynomial method. And this polynomial satisfies this condition. P of x minus f of x is at most 2 epsilon. So writing it in terms of an equation, a D-query quantum algorithm gives you a degree 2D polynomial. And one could also ask, can we go the converse? So can a polynomial give you a quantum query algorithm? I mean, if you have been following, of course, this is not true because Ambinus gave a counterexample. But the counterexample that Ambinus gave, the approximate degree and quantum query complexity grows with n. So you can't rule out the fact that this statement is true for constant d. So the statement of Beals et al. Works for d equals to 1, d equals to 2. But the point is Ambinus ruled out this statement holds for d if d scales with n. But that does not rule out the fact that this statement holds for d equals to 1 or 2. And that's precisely what Aronson et al. Did, actually. In the beautiful result, what they showed is if you have a degree 2 bounded polynomial p, that is, you start with a degree 2 bounded polynomial here, you can actually get a one-query quantum algorithm such that the expected value of the quantum algorithm is exactly this polynomial. So that's nice. So the point is they actually they answered this question for the case d equals to 1. And so that's why one-query quantum algorithms are equivalent to degree 2 polynomials. Because we know one-query quantum algorithm gives you a polynomial. And what they showed is if you have a polynomial, you can get a one-query quantum algorithm. A natural question is extended for d being 2, 3, 4. And we showed that's not true. What we showed is using our characterization, most degree 4 polynomials cannot be computed by two-query quantum algorithms. So the statement was true for the degree 2 to 1, but it's not true for degree 4 to 2. And finally, let me talk about the result that came today morning. It's by Sander Gribling and Monique Lauren. And what they showed is they tried to understand the following question. So I defined a new notion of completely bounded degree. I mean, it could just be nastily complicated, and it just could be pointless understanding this concept altogether. And so they tried to understand the question, when is it easy to compute this norm, this completely bounded norm? And if you just stare at it a little bit, and if you know a little bit about XOR games, this completely bounded norm is close to something called a jointly completely bounded norm. And this jointly completely bounded norm is extremely relevant for quantum multiplayer XOR games. And what's even more interesting is Vidic actually showed in 2014, to get even a constant factor approximation of the jointly completely bounded norm, it's NP hard. So that doesn't look that good. So it could just be that completely bounded norm of a polynomial could also just be hard to even compute, maybe, to even approximate, maybe. But surprisingly, what they showed is if you give me a degree t polynomial p, there actually exists an n to the t by n to the t semi-definite program that computes the completely bounded norm of p. And using this, they also write our completely bounded degree as an SDP. I mean, for those of you who are familiar with quantum query complexity, this is not surprising because the adversary method already could be written as an SDP. But the first thing is, again, this equality holds only for epsilon strictly greater than 0, whereas our SDP, or the SDP of Gribling and Laurent, works for every epsilon, not only epsilon greater than 0. There was another SDP, Barnum et al., where they characterized quantum query complexity as an SDP back in 2003. But what's nice about our SDP is if you'd like to certify that quantum query complexity is at least T, the certificates in our SDP are much smaller than the certificates in the one by Barnum et al. And as a final toy application of our characterization, we showed the following. So let f just be the OR function. So Nissan and Zegedi back in '94 showed that there exists something called the Chebyshev polynomials of degree root n that approximates F well. That is, they showed that the Chebyshev polynomials is close to the R function on the entire Boolean cube. So P of x minus F of x is at most a third. And what we showed is, if you look at the Chebyshev polynomials, they're actually completely bounded. This is a simple application. And in particular, what this shows is this gives you a square root n query quantum algorithm for the search problem, and this recovers back Grover's algorithm. Although this might seem totally useless because Grover is just standard these days, in the final slide, I'll tell you why I mentioned this, and I think it's interesting, actually. So let me conclude. So as a summary of our results, the motivating question was, does the polynomial method admit a converse? And we did answer that by refining the polynomial method. We gave a new degree measure called the completely bounded approximate degree that's equal to quantum query complexity. Using that, we showed most degree 4 polynomials cannot be computed by 2 query quantum algorithms. And finally, we could recover Grover's algorithm. And people also, as a follow-up work, people showed that our degree measure could be written as a semi-definite program. So there are many directions for future work. And the first natural direction is, can we construct new quantum algorithms using our technique? So if you look at how we reconstructed by Grover's algorithm, the recipe was very simple. You look at a Boolean function that you care about, go ask the classical people, tell me an approximating polynomial for this Boolean function, and try to show that approximating polynomial is completely bounded. If you can do that, then you get a new quantum query algorithm. And recently, there have been many results that actually come up with explicit approximating polynomials. Like Sherstov had a result last year where he came up with many interesting approximating polynomials for Boolean functions. So one task is that we are trying right now is just to try proving that some of them are actually completely bounded. So you get new quantum query algorithms, or maybe recover existing quantum query algorithms in our framework. And of course, another direction is to prove lower bounds. So to use the polynomial method, one thing you would have to prove is no polynomial can approximate the Boolean function, but now you just need to show no completely bounded polynomial approximates the Boolean function. Another question is, can we show that the SDP that they came up with today it actually composes in a nice way? So can you show that this equality holds? We know this equality holds for every epsilon greater than 0, but for epsilon equal to 0, this is still unknown. We don't know, as far as I know, whether quantum query composes for exact quantum query for epsilon equal to 0. And so this is a nice question to answer. And I mean, as I've been saying throughout this talk, I mean, our degree measure is better than the adversary method in the sense, firstly, it's tied up to constants. And for there are some problems like the ordered search where you would like to know the constants. And secondly, it works for every epsilon, even epsilon greater than 0. So can we use this to show separations between QE and Q2? And the final question, which I think is interesting in light of recent results, is just like the quantum query complexity, there is quantum communication complexity and log of approximate rank. So log of approximate rank lower bounds quantum communication complexity. But recently, there have been a couple of papers that showed exponential separations between these two measures. So can you have a new notion of completely bounded approximate rank that characterizes quantum communication complexity? And this would be more interesting than this work because there exists exponential separations between these two measures. And of course, one direct approach one could take is improve approximate rank to approximate block multilinear rank, and then improve it to completely bounded approximate rank. Yeah, I think all these are interesting questions. With that, I thank you for your attention.
Okay, we have time for 1 or 2 questions. Yes, the mic.
Yeah, so a naive skeptic might say, oh, well, you know, I could define a new type of polynomial degree, right, that where you just minimize over all polynomials that arise from quantum algorithms, right? Now, it's clear that something more interesting must be going on here, you know, because you can use this new characterization to solve this 4-to-2 problem and so forth. Can you sort of articulate sort of what is the sort of what is the new leverage that you get from this characterization, you know, beyond just knowing that it came from a quantum algorithm? Because
I think to us, I think the whole point was we just replaced these oracles.
Yeah.
And then it was just the magic of the C-star algebra theorem that happened in '87. And so it just happened to work beautifully for us. So even maybe I'm trying to understand why this works in the first place. But I agree with you. We don't have too much intuition. But the fact is, like the same intuition that you had earlier for block multilinear degree. Yeah. It has satisfied certain properties, just make it satisfy those properties in a degree measure. Yeah. And that's what we did.
Okay, so one more short questions.
Does the completed bounded degree give you an actual algorithm,
That's
or
a
is
good-
just prove the existence?
It right now proves the existence, but we're actually trying to come. So the point is we have to go back to this result in C-star algebra and we have to extract the unitaries out of it. And we are able to do it sometimes, but in general, we don't have an explicit algorithm. It gives you the existence of an algorithm.
In the case of Grover, do you know the algorithm, or is it the same as Grover, or is it some completely new way of looking at that problem?
We don't know.
Okay.
We don't know.
Okay, so there's this extension of the adversary method, the multiplicative adversary method, which generalizes both the polynomial method and the adversary method. I have a feeling that this might be equivalent to your completely bounded approximate degree. Have you looked into that?
So this is your paper with Lloyd McNeil. Yes. Yes, I have looked at that. When I read through it, it didn't seem like they were equivalent, but it might be. But when I have looked at this paper, and it didn't seem equivalent at first sight, actually.
Thanks.